I am Reinhold Noe. In my lab I have a Novoptel LU1000 laser unit. It is connected to an EPS 1000 polarization scrambler. The output of the polarization scrambler is connected to PM 1000 polarimeter. Here I've opened the graphical user interface of the scrambler and of the polarimeter. In the polarimeter graphical user interface I've opened the Poincaré sphere window. Now I can see here the current measured polarization. I can wiggle one fiber or another fiber and I see that this moves. You can see essentially the same display also on a monitor which you connect to the polarimeter, so a computer would not be needed. I clear the trace and I look at my settings. The calibration parameters of the polarization scrambler are chosen corresponding to the laser frequency which I've entered, and the polarimeter is set to the same frequency. The polarimeter has an averaging time exponent of 2. This means the sampling time is 10 nanoseconds times 2 to the power ATE. So in this case 40 nanoseconds corresponding to 25 megasamples per second. I can do the following settings also with the push buttons of the instruments, but here I do it in the graphical user interface. I want this polarization to move and I enter now, for example, 10 radian per second, and forward direction, you see this is moving. I can also rotate in backward direction, or I can stop this. To make settings convenient, I choose here a peaked scrambling speed distribution. I enter, for instance, 100 kiloradian per second, and this instantly sets the wave plates at various speeds. I have 3/4 wave plates, 1/2 wave plate, 3/4 wave plates. Poincaré sphere has filled instantly. I stop now here a few wave plates. I go back to user defined to stop a few wave plates, and I see now that the input polarization is changed at speeds on the order of 1 kiloradian per second, and it fills fairly quickly. Meanwhile, I have stopped the 3/4 wave plates at the input, and only the half wave plate is running at 100 kiloradian per second. 100 kiloradian per second is the speed which occurs if this polarization runs on a great circle. To achieve this, I can go to the position control window and I select the input polarization accordingly that this is roughly a great circle. So now we have it. I've opened the state of polarization speeds distribution window. I've set tau equals 2 times the sampling time 10 nanosecond times 2 to the power clock exponent. And 2 times 10 nanoseconds to the power times 2 to the power 6 gives me 1.28 microseconds. The fastest speed I can measure with this is 6 megaradian per second. I can start the restart the histogram, and this looks fairly much the same. I can also display this in logarithmic scale. When I set the input polarization, I can generate circles of all radii, and you see that the speed distribution gets also lower speed components. This has been rescaled horizontally because a few, but very few samples with higher speed also occurred. In linear scale you don't see this any longer. So now I'm at a polarization where the radius is smaller so that this speed dominates. With the output polarization controllers, also 3/4 wave plates, I can orient this to be anywhere on the Poincaré sphere. I can reorient this. I will now run all wave plates, for example, like this, and I have now circles of all radii, and all orientations, and the Poincare sphere fills quickly. I restart my histogram. This is the typical peaked speed distribution which I obtain. We think a peaked speed distribution is very useful for the testing of coherent transponders, because usually they are made for a maximum design speed of polarization changes which are permissible, and it makes sense to test them as often as possible near to the design speed, and only if you set the peak at a higher speed, then the reception or signal recovery will of course break down. According to our experience, high polarization speeds are about 50 times more frequent than in the case of a quasi-Rayleigh distribution, which I can also choose. I do it here with the same design speed. I restart the averaging, and now I have a close to Rayleigh distribution. The fast polarization changes occur only rarely. But maybe you want to generate a speed distribution of your choice. It is best to do this by superimposing several peaked speed distributions. This way you have the greatest freedom. I go to synchronous triggered scrambling. I choose table mode waveplate speeds, and I set a dwell time of 100 milliseconds. I insert entry behind, well, behind no entry, so this is my first entry in the table. I go back to rotation control, and I choose now a smaller speed, for example 50 kiloradian per second. This gives me a histogram with a maximum near 50 kiloradian per second. I go back to the synchronous triggered scrambling page. I set now a shorter dwell time, for example 30 milliseconds, and I insert entry behind. I save my file under the file name 2peaks.txt, and I open it to see what's in there. I have two entries in table mode speed. 3 is backward rotation, 1 is forward rotation. The half wave plate rotates forward. All the quarter wave plates in this case rotate backward. These are the speeds of the wave plates. The quarter wave speeds are radian per second with 2 digits, like you can see here. The half wave plate speed is kiloradian per second with 2 digits after the decimal point. Last entry is the dwell time in nanoseconds. 100 million or 30 million nanoseconds are the dwell times. Now I'm running my two different speed distributions alternately, which means that I get this distribution with two speeds. To do so, I set synchronous triggered table execution instead of the usual continuous waveplate rotation. I set continuous trigger, so this is being triggered all the time, and I set to table mode. This means I continuously go from entry 1 to entry 2, see the current dwell times here. I've meanwhile gone back to the continuous waveplate rotation, and in rotation control I've set 10 megaradian per second peaked distribution. You see this is not completely smooth, but that's a minor issue because still most events are at a high speed. I needed to set the clock exponent lower so that the maximum scale is, for example, 100 megaradian per second. I look again at the Poincare sphere. It fills instantly. The filling is mainly determined by the quarter wave plates, which run with speeds on the order of 100 kiloradian per second each, because the 10 megaradian per second half wave plates just causes small or larger circles. So you must not have small circles for longer times, and this happens only if these waveplates have moved sufficiently. Thank you for your attention.